Our star, the Sun, was born in one about 4.5 billion years ago. So one of these clouds collapsed upon itself under its own gravity to form a globe. This then spiralled into a disk, becoming our solar system. Amongst the spheres of rock and gas, only one gave rise to life: Earth. But could this magnificent living planet really be unique amongst the stars?
We are an incredible miracle. Stars died to create the chemical elements in us, and somehow we rose to consciousness and asked the question, why are we here? Where did we come from? Are there others like us? This is the quest that we have been on from the moment we were conscious as a species. It is our destiny to answer these questions. We could not possibly have been forged in the dying throes of stars and created in that tremendous explosion, and now turn our back on looking for other creatures that were formed the same way.
Artemis, this is Supply Shuttle Aurora, X-Ray Hotel Golf. Guidance systems OK. Confirming request for docking.
Affirmative, Aurora. You are go for docking. Fusion Bay 04. Artemis log, October 4, 2157. Launch minus 25 days. I am in the final weeks of construction. More than 1,000 men and women have toiled in space for a decade to build me. My memory fields are online and ready. I am Artemis, the artificial intelligence that will pilot this mission. Engineering works are almost complete. Fuel cells are arriving daily. Soon, all eyes on Earth will be trained upon me. My mission carries the hopes and dreams of humanity. I do not dream, but I have been given the knowledge of all humankind. Its science, its art, its wonder, all packed into my memory banks. My mission is to guide this ship 4.7 light years to reach the exoplanet Minerva B. My objective is to find evidence of life.
Life first emerged on Earth almost 4 billion years ago. Shaped by the ever-changing forces of geology and climate, life has evolved with extraordinary richness and resilience. We have explored every corner of the Earth, and we have been amazed at the diversity of the natural world. As our technology improved, we inevitably turned our gaze to space, looking for life on nearby planets. But despite our ingenuity, we came back empty-handed. But what about planets beyond our solar system? Could life of some kind exist out there amongst the stars?
I was a graduate student when the very first planet was discovered.
Natalie Batala is part of a new generation of planet hunters, looking for worlds like Earth, but in other solar systems.
I would say my biggest hope was that we find an Earth-sized planet orbiting a star very much like our own sun, in a similar orbit where the conditions for life might be just right.
5, 4, 3, 2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
In 2009, NASA launched an orbiting telescope, Kepler. Its mission was to search for Earth-like planets. It carried instruments sensitive enough to detect the infinitesimal dimming of starlight as distant planets passed in front of their star.
The difficulty is that this dimming of light is very, very small for a truly Earth-sized planet orbiting a sun-like star. It's 1 part per 10,000. The analogy I like to give is to imagine the tallest skyscraper in a city, and it's nighttime, and every light is turned on in every room. And one person walks over to the window and lowers the blinds by about 1 centimeter. That's the dimming of light that we have to be able to detect.
Kepler has surveyed just a small region of the Milky Way, but its discoveries have been stunning.
The first light image was magnificent. It was like champagne filling a glass, just these millions of stars that I had been studying for years before Kepler even launched, filling the screen. And there were actually already a couple of giant planets that were in Kepler's field of view. We've learned that every star that you see when you look up into the sky at night has at least one planet. The other thing that we have learned is that nature makes small planets more efficiently than large planets. The third thing we've learned has to do with the fraction of stars that harbor Earth-sized, potentially habitable planets. And we can make the bias corrections to determine that number. And what we find is that it's about 22 to 25%.
So every star in the sky has at least one planet, and of those, 1 in every 4 is a candidate for life. Kepler has revolutionised the way that we see the stars.
Artemis log, November 22nd, 2157, Day 0. Mission Control, this is Artemis. Systems report go for dock departure.
Roger, you are go for leaving dock. Launch in T-minus 30 seconds.
Firing attitude control thrusters.
Artemis, you are go for position reset. All systems are go for launch in T-minus 10 seconds. 9, 8, 7, 6, 5, firing DFD drives. 2, 1, 0. We have launched.
I'm heading for the Minerva system first interstellar mission to an Earth-like planet.
We are searching for a planet that has just the right atmospheric conditions to support life. Although Kepler has identified thousands of Earth-sized planets, so far it appears that very few of them may hold the essentials needed for life. At least, life as we know it. Francois Forget models the climate on distant planets, predicting if it's suitable for life to emerge.
La vie a besoin d'eau. Alors cela dit, de l'eau, on pense qu'il y en a presque partout dans l'univers. Mais essentiellement, en fait, si on regarde sous forme de glace. Et c'est pas ça qu'il faut. La vie telle qu'on peut l'imaginer, chimiquement, et surtout telle qu'on pourra la reconnaître, ce qu'il faut vraiment, c'est de l'eau liquide. Et ça, c'est pas évident, parce qu'il faut les bonnes conditions de température, de pression.
Our rivers, lakes and oceans exist only because Earth orbits at an ideal distance from the Sun, within a region called the Goldilocks zone. Not too cold, not too hot, but just right. It's this fortunate orbit that makes all life on Earth possible.
D'ailleurs, on calcule que si on déplaçait, avec nos modèles, si on déplaçait la Terre de quelques pourcents vers le Soleil, en fait, le climat s'emballerait parce qu'il y aurait un peu plus d'énergie solaire, les océans seraient plus chauds, plus de vapeur d'eau, plus d'effet de serre, et hop, très vite, on peut basculer complètement, les océans peuvent totalement bouillir et s'évaporer. Et inversement, avec la Terre telle qu'on la connaît actuellement, si on la déplace de quelques pourcents vers l'extérieur, on l'éloigne du Soleil, eh bien, il va faire plus froid, il y aura plus de neige, plus de glace, et cette neige réfléchit le rayonnement du Soleil, ce qui fait qu'il fait de plus en plus froid, et ça s'emballe inversement, et la Terre peut être complètement couverte de glace, ce qu'on appelle une Terre boule de neige. Ce qui fait que la Terre est particulièrement propice à la vie, c'est pas seulement qu'elle est couverte d'eau liquide, d'océans aujourd'hui, mais surtout qu'elle a été pendant toute son existence, pendant 4 milliards d'années, ce qui a permis à la vie de naître et d'évoluer.
Astrobiologists now believe that our best chance of finding life on distant planets is to search for candidates that are just like Earth in the Goldilocks zone around a star.
I was a child around 10 years old, and I was on a camping trip with my family. And I stepped outside the tent in the middle of the night, wandered out, and I looked up, and wow, I saw so many stars. Thousands of stars. I had never known this existed, and I was thinking, like, why didn't anyone ever tell me about this? How do you convey to another person the beauty and the majesty of the night sky? And I just wondered, what's out there? What could possibly be out there in our night sky? When I want to think, I come here to the Great Lake. And I look out on the water, and I just think about how wonderful life is, how fragile life is. It gives me hope that there's another planet out there where life could really thrive.
6, 5, 4, 3, 2, 1.
Sarah Seeger is Deputy Director of TESS, an orbiting telescope launched in 2018. She leads a team of young planet hunters.
Looking at a planet's atmosphere far away is the best way we have to find signs of life on another world. Because the gases that life produces, here on Earth actually, imprint in our atmosphere in a very significant way. And so it's just amazing to think that on another world we can do the same. TESS wants to find stars that are closer, right in our neighborhood, actually, so that we can study the planet atmospheres and get way more detailed information on those planets. The camera has a lens assembly of 7 lens elements that refracts starlight onto a detector. And together they make a giant strip. When you think of the sky as a sphere, from the bottom of one hemisphere all the way up to the pole. After 1 year of doing that, TESS will flip to the next hemisphere, and it will then do the same thing. And so over 2 years, TESS aims to study the entire sky.
TESS will identify an exoplanet with an Earth-like atmosphere and the one essential factor we believe is crucial to life: water. It is the search for water on other planets that inspired interplanetary explorer Steve Squires.
It was only for graduate students, and I was an undergraduate, and I nearly got thrown out of the class the first day. And got to be, I don't know, 3 or 4 weeks into the semester, I'm thinking, I better start thinking about my term paper. And there was this place then, at the time, called the Mars Room, and it was a place where the pictures from Mars were stored. And I went in, and I thought I'll sit down for 15 or 20 minutes and flip through some pictures and see if I can come up with an idea for a term paper. You know, it's not like today where pictures come down from Mars and bang, they're on the internet an hour later. There were only a few dozen people in the world who'd seen these. I didn't understand what I was looking at in the pictures, nobody did. But then I would see in the pictures, you would see these little valleys that just looked like they had to have been carved by liquid water. And I was in that room for 4 hours, and I walked out of there knowing exactly what I wanted to do with the rest of my life.
Waiting for information from spacecraft.
In 2004, Steve Squires led the NASA team that landed the Spirit and Opportunity rovers on Mars.
Holy smokes.
They came with a 3-month guarantee, but Opportunity was still going strong 15 years later.
The thing that has driven the focus of exploration in this solar system has been the search for other forms of life. And so I think the motivation is going to be the same thing. I think the motivation when you go to other star systems is going to be fundamentally the search for life.
Artemis log, December 8, 2157. Ahead of me is Mars, the first planet explored beyond the shores of Earth. Below is the Viking colony that has now been there for 90 years. Population 1,536. The brave pioneers of the colony sent me good wishes for the journey ahead. I'm sure some of them would like to be joining me. Navigation across 50 trillion kilometres requires intricate calculations. I have plotted my course from Earth I'll slingshot off Jupiter, then steer for Minerva. Its orbital period is 39 Earth days. It lies within the habitable zone. Spectrometry reveals an atmosphere that contains water, carbon dioxide, ozone, and methane in promising concentrations. My mission of finding complex life has every chance of success.
I get up each day with joy. You know why? Because I know that day I'm going to learn something I didn't know before, and that my picture, my overall tapestry of who we are, who I am, what our species is, and how we got to be that way will be lifted up.
NASA's chief engineer of planetary flight systems, Gentry Lee, is a pioneer of exploration. He's 75 years old, and he's dedicated over 50 years of his life to exploring other planets.
Someone asked me one time if I had to describe the excursions above the threshold of joy in my life, would there be a lot of them or just a few? And I said, I can give you the two categories right away. The birth of my children, and I now have 8, and when a spacecraft that I had a major role in achieved something successfully. And there's also been 8 of those.
Gentry Lee and Steve Squires helped forge the trail into the solar system. But a new and even greater test lies ahead. Now we must venture further into our galaxy. And there we will confront extraordinary challenges.
The problem is they're so far away. You know, you have this wonderful notion that, yeah, we'll travel to the stars, but they're just so far away. To travel to a star that's 10, 15, 20 light years away in a time that is not immense compared to a human lifetime. You're talking about accelerating a spacecraft to a significant fraction of the speed of light, and that's really hard.
It is hubris on our part to imagine that we can sit today and define all the steps that lead us to this plethora of technology advances that we need in the future to build an interstellar spacecraft. Rather, let us do the following thing. That spacecraft must communicate, it must navigate, it must have propulsion, it must have the ability to take data. It's as if Henry the Navigator, as the King of Portugal, had said, I don't even know yet what kind of ships I need to build or where they need to go. Let me just start with an idea. What floats? That's where we are. But it is so exciting because at this moment, with the Kepler discoveries, there is a vastness out there for us to explore that will challenge us for generations.
Artemis log, December 12, 2157. Passage through our solar system is progressing well. The storms on Jupiter are intriguing. I will now accelerate toward 20% the speed of light. $216 million kilometers per hour. Shortly, I will pass my interstellar ancestor Voyager 2. It recently celebrated its 180th anniversary. I will make the journey to reach the exoplanet Minerva B in 48 years and 6 months.
Engaging interstellar passage mode. Retracting transceiver.
Our imagined exoplanet, Minerva B, is 4.7 light-years from Earth, or 45 trillion kilometres. The quest to design a ship that can traverse such vast distances will test our next generation of explorers and demand of them the ultimate commitment. For they may not live to see the fruits of their labour.
You're asking people to devote their careers, their lives, to something they will never see to fruition. Now, that has happened. That has happened a few times in human history. Some of the great cathedrals of Europe took longer than a human lifespan to build. People felt guided by a higher power when they did that. But it takes something extraordinary to motivate people to do that kind of thing.
People tell me, oh, how are you imagining interstellar spacecraft? And I say, you have forgotten the fundamental precept of all engineering invention. Necessity and desire are the mother of invention. Once you set your eyes on a planet out there, Earth-like, in the Goldilocks zone, once we think we have a chance, we will develop the techniques for interstellar exploration. And the payoff once we get there is beyond belief.
Science fiction enabled starships to enjoy high-speed interstellar and even intergalactic travel, with their propulsion systems limited only by the imagination, with a sprinkling of real science. However, reality has so far kept our own spaceships limited to admirable but impractical speeds. Voyager 2 has taken over 40 years to reach just the edge of our solar system. Although it's the fastest and most adventurous spaceship yet, it would take more than 80,000 years to reach our imaginary planet of Minerva B.
When I was about 10 years old, I had one of these department store telescopes, learned how to use it, took it out one night, and focused it on what I was told was the planet Saturn. And when I lined up the viewfinder and held it still, and I could see Saturn and its rings, at that moment, I felt a calling. And that calling was to learn about how to get there.
Les Johnson found his calling at NASA's Marshall Space Flight Center. For 20 years, he's been researching interstellar propulsion.
Nature is kind to us in the regard to what options we're going to have to get to the stars. Nature has said, you smart people, you can figure this out. It's just going to be really hard. It was difficult enough to go to the moon. We're sending probes to the different planets in the solar system. But to take that leap to go to the stars, the distance is just so much further and requires so much more energy that it's just going to take some time.
Chemical fuel rockets, like Saturn V, have been the workhorses of space exploration. They got us to the moon in just 3 days. But to reach another solar system in one lifetime, we'd need to reach 20% of the speed of light. At that speed, a trip to the moon would take just 7 seconds. Now, that kind of engineering is a huge challenge. So scientists have imagined some wild propulsion technology, including antimatter drives.
As any good Star Trek fan will know, right, on the Enterprise, that's what powered their warp drive. Of course, warp drive is science fiction drive, but if you think about antimatter, it's real. When matter and antimatter come in contact with each other, they annihilate. And it essentially is the perfect E = mc² moment is released as energy. And this is where it gets tough. If you look at the total amount of antimatter produced globally today, it's on the order of nanograms. You would need on the order of kilograms, perhaps up to a ton of antimatter to drive a starship. That's not something I want to do on the Earth, because the amount of energy released if that ton of antimatter met a ton of matter would be catastrophic. I look back at the history of science and technology, and if you had asked my counterpart 200 years ago, going to the moon, the answer would have been, that's inconceivable. We don't have any idea how to do that. It's just a matter of learning how to do it. So no, I don't think it's too hard. Do I think it's really, really hard? Yes. I think it'll be the hardest thing that we humans will ever have to do, is that challenge of going to the stars.
We may already have some potential solutions. At Princeton Satellite Systems, engineers are working on technology that could take us to the stars.
My brother will tell the story that I'm the only person he knows that's actually doing what they thought they wanted to do in high school. I identified aerospace engineering. I picked colleges for aerospace engineering. I've been doing aerospace engineering ever since because it's really fun and challenging. Space is cool. The exhaust velocity that we have is only about 100 kilometers per second. And yet you can't get there fast unless you got some meaningful thrust.
Right, so you would...
Stephanie Thomas is principal investigator in a NASA-funded program to build the world's first direct fusion drive, a combined energy source and propulsion system.
We want to reach a neighboring star in the neighborhood of 5 light-years distance. We want to bring 10,000 kilograms of payload, that's 10 metric tons, and we need to do it with an exhaust velocity that we can actually achieve with an engine.
The direct fusion drive runs on a dense isotope of hydrogen called deuterium, and it can be found everywhere, in water. The drive unit is compact, just 1 metre wide and 10 metres long, perfect for mounting in a starship.
We think that we can build the next generation machine in maybe 5 years. It will take at least another 5 years to build a prototype that you could launch. But definitely 15 years at the outside, we think we could have one and put it in space. At some point, we have to visit the stars. We're never going to just sit here and be content, you know, even when we're visiting the planets, because we want to know what's out there. Everybody wants to go to the stars someday.
We have the motivation, and now it seems we may have the speed to reach Minerva B, But navigating the vast distances of interstellar space involves even more challenges, some of them beyond mere human capabilities.
When great distances and the speed of light get involved, it becomes a very, very different sort of experience. Simple words like now take on a kind of a different meaning. I remember when we were landing on Mars, from when you hit the top of the Martian atmosphere to when you're on the surface, takes about 6 minutes. At that time, what we call the one-way light time, how long it takes a signal to travel at the speed of light from Mars to Earth, was 10 minutes. So we're sitting there in the control room, and we're watching the radio signal, and we're watching the spacecraft begins to slow down and curve down in the Martian atmosphere, and it's just at the top of the atmosphere. The reality is, out at Mars, it's been on the surface for 4 minutes. And it may be a happy, healthy rover, or it may be a smoking hole in the ground, and I don't know. I'm not seeing reality at that moment. Magnify that. So instead of 10 minutes, it's 10 years.
Welcome to the Ops Lab, Francesca. Thanks for coming. You ready to walk on Mars?
Yeah. We're gonna walk around on Mars, Francesca.
You see the mountain over there? I bet your dad can tell you the name about it.
So what is that?
I think it's Curiosity.
I think you're right.
I don't know where the laser is.
It's also in that same box. So what do you think we do with the laser?
Well, I don't know.
It goes zap and hits one of the rocks, and right at the end where it zaps it, it turns it into a gas, and then it analyzes what that gas is made of.
Yep.
Yep. All right, so what do you want to do now?
Well, let's go to Mount Sharp.
Okay, let's go to Mount Sharp. The first and most important thing, a spacecraft that goes to another star to survey planets and look for life must be basically autonomous. It must be artificial intelligence raised to its highest level. All the navigation would have to be on board. All the algorithms, the computations of the orbit, the computations of the maneuvers to get to the right place, what stars to look at is for this year, what stars to look at for next year. What we would have to do is extend our minds to imagine all the possibilities that they might run into. And we would spend literally years building this hierarchy of possibilities into this artificial intelligent machine. It would have to know at all times how well all its critical systems were doing, and how to fix them if they weren't working right, and how to replace them if they couldn't be fixed. What a challenge.
Warning, warning, warning. Alter course. Warning, warning, warning.
Micrometeorite field detected. Initiate shield protection maneuver. Fire ancillary thruster. Reposition.
Warning, warning, warning.
There will never be an artificial intelligence system that we will be able to build that will be faultless. So one of the most important characteristics of this autonomous system is to be able to recognize its own mistakes. Talk about being human.
Self-diagnostic initiated. Damage report. Reverse thrust radiator damage, minimum. Transceiver, check. Initiating redundancy system reboot.
Artemis log, January 20, 2170. AI reboot initiation successful. I'm back online. Analysis, my self-repair systems should be able to fix the damage. Whilst fear was not part of my design, I'm learning that it is an important function of self-preservation. I will need to mimic it. Any further damage could be catastrophic, ending the mission. I've gone off course. It will take me several days to reset my waypoints.
The great marvel and the paradox of wide open spaces is that they make us look inwards. Confronted with the infinite, we reflect upon the self. Where do we come from? Why are we here? Are we alone?
As a young child, I was mostly interested in philosophy, and I used to wander into the hills of the village where I was born. I was interested in questions about our existence, involving also the big picture, which is us being in the universe. The question is, how did we come to be inhabiting this two-dimensional surface on a piece of rock that we call our home, the Earth, near a star like the Sun, that is one out of tens of billions of stars in the Milky Way galaxy, that is one out of trillions of galaxies in the universe. How did this all come about? And are we alone in particular?
Avi Loeb grew up, but he never grew out of his fascination with the fundamental mysteries of life. Today, as Chair of Astronomy at Harvard University, he seeks to understand our place in the universe by combining philosophy and science.
The most fundamental question that science can answer is, are we alone? The answer to this question could have implications to all aspects of our life. It could change people's religious beliefs. It could change the way we think about our place in the universe. It could change philosophy, linguistics, in terms of communicating, if this other form of life is intelligent like us. I'm agnostic about whether the answer is yes or no. I think we should explore rather than have a prejudice, just like Columbus went out to discover the new worlds. The answer lies in space.
Initiating staging separation of reactor propulsion unit. Firing reverse direct fusion drives.
Artemis log, March 18th, 2181. It is time to start slowing down. It is 23 years and 2 months since I left Earth orbit. Minerva C is a gas giant similar to Jupiter. As I approach the system, I will use its atmosphere and gravity to reduce speed and alter course.
All life on Earth is based on organic molecules centred around the element carbon. Scientists believe that this organic material was created during the birth of our galaxy from a carbon-rich disk of dust and gas. This suggests that these building blocks of life may be present in the birth of all solar systems.
Looking back at our own Earth and why we have this rich, biosphere, well, we think it all started with having all this organic material that we are made up of, that was delivered from space, from comets and from asteroids. So we were thinking about the likelihood of life elsewhere. We're pretty much thinking about the likelihood of having that same scenario taking place.
High in the arid mountains of the Atacama Desert in Chile is a new telescope called ALMA. It's here that Karen Oberg is on the hunt for these precursors of life in the birth cloud of a distant solar system.
ALMA consists of 66 individual telescopes that's all working together. It operates at millimeter wavelengths. And millimeter wavelengths is we can detect molecules, some of these organic molecules that we are so interested in.
In 2015, ALMA's gaze turned towards a young star in the throes of birth, wrapped in a disk of gas and dust from which planets were being born.
We see this dust and gas that's surrounding these young stars, and what's even more exciting, we see that they often have little lanes or tracks in them where it looks like planet formation is going on right now.
ALMA revealed a stunning discovery in that infant star.
So there are two things that are significant. One is that, first of all, we're seeing these more complex organic molecules, and we're seeing them in a system where planets are forming right now. And that immediately is telling us that when planets form there, they will form in a bath of these complex organic molecules. But I think what's especially caught our eye here is that the chemical composition of this disk looks so similar to what we think that our own solar disk once looked like. Chemistry is awesome. It's the reason that we are alive and that we're here in the first place. So far, it's only one system apart from our solar system where we have this chemical information. But my intuition would be that it's going to be very common. This kind of chemistry is going to be almost universal.
The same organic molecules essential to all life on Earth are out there amongst the stars.
Artemis log, March 19, 2206. The Minervan sun lies ahead. I was designed to explore, to research, to understand. That time has come. What will I find?
Second staging separation initiated. Trans-Amouroux orbit position lock. Earth signal position confirmed.
I can now see Minerva B. It is beautiful. It is time for me to take a close look at my new home. There are many unknowns.
Deploying survey and GPS satellites.
Over the coming months, I'll collect telemetry from my satellites and begin mapping terrain and naming locations. I must calculate atmosphere, gravity, and climate variables before selecting a favourable landing site.
Curiosity about the unknown is part of what makes us human. It has driven our history and progress. But exoplanet exploration will test us in unique ways. We cannot predict what we will find, so our robot explorers must be prepared for anything.
Exoplanets present a real challenge because there's so much uncertainty. So knowing whether or not you're going to find a cliff face versus a desert versus an ocean versus an ice tundra, we may not know when we launch. So you've got to design your system to survive and operate in all of those possible conditions. With planetary exploration, we started with a large robot that was very stable, very safe, and now we're beginning to take more risk. We're trying to get to new places, trying to shrink down the size of the platform, do more with less.
It's a pretty perfect ledge over there.
It's just the sort of thing other rovers can't fit into.
We work on extreme environment robots. So these are things that are meant to fall. We want them to be crash-proof. So you can see this whole structure, even the wheels, are meant just to bounce.
Some of our robots are designed to climb up different surfaces. So we have a claw-inspired robot that uses sharp hooks to grab onto the rough surface, kind of like an insect or a rock climber would scale up a cliff. We also use electrostatics to stick to surfaces. So this is like rubbing the balloon on your head and it sticks to the wall.
So this is a Kagome structure, which would be hard to fabricate through any other means than 3D printing. What's truly unique about this structure is the material. We have created a material that has mechanical properties similar to that you see in biological tissues. We have already, with this system, developed swimming robots.
There is a lot of work today in underwater robotics and in robots that can go between dry surfaces and water-like surfaces. Wherever we find water on Earth, we find life. So we have a strategy that we've used on Mars called Follow the Water. I think we're going to use that same strategy when we visit an exoplanet. Look for life in the ways that we conceive of life now, and try and be open to seeing versions of life that might be very different than our own version here on Earth.
I'm about to make my first attempt at landing on Minerva. A storm front is cleared, I've located a favourable landing site about 1 kilometre from Mount Armstrong.
Final telemetry checks.
Check.
Deploying Lander 1.
Go. Following the failure of my first deployment, I've taken more detailed measurements, revised all calculations, and discovered my mistake. Now, I believe I am ready.
Deploying Lander 2. Ballistic parachutes. Go. Firing retro rockets.
Mission Control, we have landed.
What kind of life could we find on another planet? That's a question that has long intrigued Chris McKay, a planetary scientist.
My intuition is that the universe is full of life. There's no reason fundamentally it might not look like Earth with vegetation and animals. Well, the question that I'm interested in is really the start of life. And on Earth, we see for a long time life was just microbial, but all the essential features of life were there. Nothing new was invented when life became trees and animals. That was just morphological. That's just window dressing. Everything interesting with respect to biology was present when there were no trees and no animals and life was just microscopic. The DNA was there, the amino acids was there. All the biochemical machinery that makes life life was there. So when we search for life on other worlds, I tend to focus on this early, simple step. We're going to look at the biochemistry. We're going to look at the molecules that life is made out of.
May 27th, 2206. Minerva surface. My lander may now make autonomous decisions and is observing local terrain. We have successfully deployed 3D printed drones and spider bots. They are providing my vision of the planet. It is data-rich, and it is fascinating. Mission Control, We have confirmed a key objective. There is liquid water on Minerva B, significant quantities. I am confident of further discoveries.
Sampling amino-rich water. Depositing sample. Sample analysis. Alien amino acid detected.
Samples contain complex biomolecules. The structure is unfamiliar, but appears to be analogous to DNA. With a high degree of confidence, I can confirm this is a life form. I have succeeded. We have succeeded.
Life form detected.
This isolated, determined little plant appears to be similar to a succulent. This is an important development. Evidence of the emergence of higher life forms. We appear to be observing the result of evolutionary processes.
What are the processes that might drive complex life? Well, we have only our own planet as a guide, but we can at least speculate about possibilities of evolution on other planets. Something amazing happened on Earth 540 million years ago. Life took a giant step forward, and the evidence can be found here, in the Canadian Rockies, amongst the fossils of the Burgess Shale. These rocks contain some of the first evidence of multicellular organisms on our planet. The first eyes. The first hard body parts, bones and exoskeletons. The first lateral symmetry. The first efficient guts, even the first brains. Sculpted in the finely packed sediment of an ancient ocean is the turning point in the evolution of advanced life on Earth, the Cambrian explosion.
As far as we know, life dates back at least to 3.4 billion years ago. And it wasn't until about 540 million years ago that we have the Cambrian explosion. And that fundamentally changes the planet. It goes from a microbial world to one that is literally teeming with animals, and not just small and simple animals as we would have originally imagined, but instead we have a whole array of complex life, still only in Earth's oceans at that time, but all of the major groups of animals appear geologically instantaneously.
It is apparent that evolutionary processes have been present on Minerva B. There is evidence of historical climatic shifts similar to Earth.
Ancient sediment survey. Mineral sample scan. Fossil analysis. Reconstructing.
Comparison evaluation suggests analogous to a Komodo dragon. Amphibious or terrestrial origin is undetermined. I shall name it Archaeopleicus problematicus. Perhaps an event such as an ice age has caused the extinction of these larger creatures. Due to the atmosphere being much thinner than Earth's, solar radiation levels are higher, limiting what can survive in the daytime.
Bioluminescent organisms. Predator.
Camouflaged predators, a key indicator to the acceleration of evolution. It is time to broaden our search. We must follow the water.
We know that life is possible given certain chemical and physical conditions. We know it's possible because it happened here. I would expect to find life elsewhere.
Astrobiologist Lynn Rothschild expects that the oceans would be the primary target for finding life on an exoplanet, just as they were the cradle of life on Earth.
Much of the diversity of life has occurred within oceans like we have here today. In a lot of ways, water is a much better environment for life. When the temperature gets very cold or very hot, the water temperature stays the same. And so if you're living in the water, you're protected from much of the changes in temperature. Say we could go to a planet that had maybe 3 times the gravity of the Earth. If we were in the water there, it wouldn't be too dissimilar from being in the water here. Maybe what we've gone through is highly unusual, and on other planets or watery worlds, it happens in a completely different way.
However, there are literally billions and billions of galaxies. So if you start multiplying up the numbers, even if the chance of life evolving is fairly small, there's so many places where it could evolve. Surely life must be common in our universe. I would be shocked if it weren't.
first month on Minerva B has yielded many discoveries. Its seasons are shorter than Earth's. The life forms I have found are remarkable, but so far I've found only fossilized evidence of advanced animals. It's time to explore beneath the surface.
Water temperature 12 degrees Celsius. Deploying swim bots.
This is what we hoped for. The oceans are full with complex life. Some familiar, others strange.
Early philosophers thought that the sun moves around the Earth, that we are at the center of the solar system. Took a lot of effort to demonstrate otherwise. So then we realized, okay, we're not at the center of the solar system, but perhaps the solar system itself is at the center of the universe or the Milky Way galaxy. Turns out that it's not. The sun is one out of billions of stars moving around the center of the Milky Way. And the Milky Way is moving through the universe. There is no center to the universe. Nevertheless, at this day and age, many scientists believe that we are at the center of the biological universe. Based on lessons from the past, I would tend to believe that we are not special. Primitive life exists and is very ubiquitous throughout the galaxy, throughout the universe. And even intelligent life is common. There might be even superior forms of intelligence. And if we ever find them and communicate with them, we might ask them to answer questions to which we don't have an answer.
My mission has accomplished its objective. Finding life forms on the first planet we explored means that life is almost certainly plentiful throughout the universe. The discoveries have provided many answers to questions scientists have been pondering for generations, and posed many questions that the next generation of explorers must answer.
The part of this that is thrilling to me is that our best attributes, if done correctly, exploration at its finest, have been programmed into an extension of our species. It belongs to no single individual. It is, more than anything else, a symbol of humanity working together to create something whose only purpose is to gather knowledge. What a beautiful thought. And after a long period of time, finally the moment of truth is coming. And more than likely, the people that designed it originally are no longer alive.
This one's cool over here.
And they have passed on this thrill, this passion to their children and perhaps even to their grandchildren. So would you like to take a hike here?
Yeah, let's go.
All right, where do you want to go?
Let's go up the hill.
Okay, we'll go up the hill. Will it be that they found life? Will it be that they found a planet where we could someday exist? Whatever it is, it will be a historical milestone unlike any other.
I've wanted to find signs of life on other worlds for as long as we know, actually. Even back to the Greek philosophers. Anything is possible within the laws of physics and chemistry. And any planet we can imagine is probably out there somewhere. Nature is boundless, like in its variety of exoplanets. I definitely am an explorer. In many ways, probably more than a scientist. Because I just love new things. The desire to travel and to explore and to go somewhere new, I think, is so strong that someday someone will find a way to make it happen.
That moment when something new is revealed that no one's ever seen before, that's just glorious. That's exploration. And it's going to happen when we go to other worlds around other stars in a very, very, very big way. And we'll be sitting back on Earth, and that downlink will come, and the video or the pictures or the spectra or whatever it is are going to come up on a screen, and everybody's jaws are just going to drop.
Mission Control, this is Artemis. We are not alone.
In breaking news, the first transmission from Captain Artemis, pilot of the starship Minerva, has reached Earth, along with breathtaking images of extraterrestrial life. The mission leaders
This has been a journey of the imagination. But one day soon, very soon, Artemis's journey will be real, and our questions will be answered. The possibilities for life are built into the very chemistry of the stars. And we will learn that we are not solitary in the infinite universe. It will be the most profound moment in our history. Perhaps our science, our civilization, and our faith will be tested. As we turn our gaze back to our own pale blue dot, our home Earth, we will find a new understanding of our place amongst the stars. Will our differences and disputes suddenly seem trivial? Will we value the miracles of life more than ever before? So when you next go out and look up at the night sky, take a moment to contemplate what you see. For every star there is a planet. For every planet is a possibility. You are now looking at something different, at a sky that has a new meaning. And perhaps you are looking up at a living universe.